If that's a genuine yes and you feel good about it, you should be able to tell me the center of mass of a simple point mass system. So let's say I have 3 people all standing certain distances apart. In fact, let's say that it's 10 meters from here to here, 3 meters from here to here, and this guy is 60 kilograms, this guy is 80 kilograms, and this guy is 40 kilograms. Can you take a moment and, using what you've already been taught, tell me where the center of mass of this system is? Did you remember that because this is a position, a location, did you choose a point of reference before you started the question? Did you decide where 0 is? Okay. Is there anybody who chose to make 0 the middle? Okay. Let me ask you, if you had decided to make the middle 0, would you know how to do this problem? Okay, let's see. Because, if you made this part 0, then this guy would have been 7 meters away, and this guy was 10 meters away, correct? And if you made the other side 0, you would have had 3 meters and 10 meters. Try making the middle 0. I want to see if you can roll with a bit of a punch here. Not everybody, but a few. If we make 0 the reference point, yes, I get the whole idea. You got to figure out how far away everybody is from the reference point. That wasn't the thing I was looking for. We're going to have the mass of this person plus how far away from the reference point they are. So how far away from the reference point are they? 5. Is that 5 in the positive direction or 5 in the negative direction? Do you see what you needed to do here? This is a vector. So as soon as this became a vector, you had to decide which direction is positive and which direction is negative. Did you do that? Yeah. Not all of you. So is that what we got? All right. All divided by 180. Location of the center of mass is a vector. I tried to explain this in the last class, and I'm not sure I did a great job. So for just a moment, I want to put in placeholder values. What if each of these guys was moving? Center of mass wouldn't be staying in one place, would it? We'd have a center of mass that's moving. So to make this easier, if we assume that they're moving at a constant speed, in any 1 second, they will have changed their location. In fact, if we divide all these by just a general placeholder for time, isn't it clear that this would be the third person's velocity, x over t? And this would be the second person's velocity, and this would be the first person's velocity. If we divide both sides of this relationship by a standard fixed time, or an expression for time, what we get is the velocity of the center of mass. So if the center of mass is moving, or if the individual particles are moving, then we might be more interested in figuring out the velocity of the center of mass, which would be the sum of mi times vi for each object, divided by the total mass of the system. And I hope you notice that the top would just be the momentum of the system. Do you see that it's the sum of all the individual momenta divided by the mass of the system? You guys see this okay? So you can have a large system of particles, but still treat the system as a single object with one center of mass. I'm just rewriting that as a summation of all the momenta would equal the mass of the system times the velocity of the center of mass. Now, I could give each of these guys a speed and have you guys recalculate that. I think that's just kind of a waste of time. Are you guys okay with this idea? Do you think you need to practice on it? Okay. Then how about we do it, just stick with our example here. Let's say this guy's moving at 2 meters per second. This guy's moving at 2 meters per second. And this guy's moving at 3 meters per second. Can you tell me what the velocity of the center of mass of the system of people is? Where the center of mass isn't necessary in calculating the velocity of the center of mass, I could, if I wanted, start by finding out what the momentum of the system is. That's going to be the first person times their speed. Well, their velocity. I need to take the direction into account. Plus the second person times their velocity. Got to take the direction into account. Plus the last person times their velocity. This will give me the momentum of the system. Now, if I want the velocity of the center of mass, divide by the mass of the system. That's still just 180 kilograms. This will give me the velocity of the center of mass. All okay? How about one more example? Real quick. And when I say real quick, you've seen this problem before. I had to take it off of the last test. But considering some of you are coming for a makeup test this afternoon, I thought it'd be nice to at least bring it up. Okay. An Atwood machine? 2 masses hung on either side, one mass greater than the other. Can we agree that whatever the acceleration is of mass 1 will be the same as the acceleration of mass 2, but in opposite directions? So if I wait some amount of time, won't box 1 be moving downwards when box 2 is moving upwards? Can you write out an expression of the velocity of the center of mass of this system in terms of m1, m2, and v? I am not asking much. I'm giving you all the variables. I'm saying the system has been moving for a few moments in time. Can you tell me what the velocity of the center of mass would be? So did you decide to make up or down positive? Down's positive? All right. Yes? Yeah. Good. So, folks, all jokes aside, this was on your test last time, if you'll recall. Actually, it wasn't this question. It didn't ask what the velocity of the center of mass was. It asked what the momentum of the system was. So the momentum of the system is what's right here. That's the momentum of the system. mv for one object and mv for the other object, added together, taking into account direction. Dividing by the mass of the system gives us the velocity of the center of mass, which should be downwards, because the bigger object's moving downwards while the smaller object's moving upwards. So have we refreshed our memory about center of mass and add a little bit to it? Impulse is how you change something's momentum. In the same way that work is how you change something's energy. Do you remember our conversation about work? About if you did net work on a system, it would change the energy of a system. A lot of you mess this up because you don't have a full appreciation of which thing to use, the cause or the effect. The effect is something that you can generally measure and observe. So for net work, it was the change in kinetic energy. For impulse, we describe it as the change in momentum. Now, the cause is a force. So for net work, if I assume it's a constant force, it was the net force and the displacement of the object. That was the cause. In our conversation on Friday, we talked about the cause of an impulse is also a force applied for some period of time. Bless you. Now, it should be clear that you can be causing a change in kinetic energy and a change in momentum using the same force. That's why these things are intimately linked together. For every impulse, there's the possibility that work has been done, and vice versa. Anytime work is done, there's a possibility that there's been an impulse. On this side, both of these are intimately related to velocity. For example, we know this is going to be 1/2 mv final squared minus 1/2 mv initial squared. Well, this is going to be mv final minus mv initial. It is certainly possible to have impulse without work. It's harder to have work without impulse. And if you don't understand, it's possible that something can bounce off a surface at the same speed it hit the surface. Could you imagine if you threw a ball at a wall and it hits the wall at 5 meters per second, but bounces off the wall at 5 meters per second? Did the kinetic energy change? No. So the net work would be 0. But did the object have a change in momentum? Yeah, it was going one direction for a moment, now it's going another direction. It clearly had a change in momentum. Energy and momentum are related, but they're not the same, and therefore measure different things. Before I go into this too deeply, and I need to go into it a little more depth, let me just talk about impulse for a moment. It is possible that they could use a symbol for impulse. If they do, they choose to use uppercase J. I generally won't. I generally just write out the word impulse in the same way I wrote out the word work. Because W's been used. J is not used very much, but it is used in other places. J is used to describe current density in circuitry. The right side of this is momentum. So the units are kilograms, meters per second. There's no special name given to that. However, the right side is Newton seconds. These are the same units. To be sure, a Newton is a kilogram meter per second squared. Times seconds gives you kilograms meters per second. So they are the same unit, but they can give you impulse in terms of Newton seconds. They can even give you momentum in terms of Newton seconds if they'd like. So don't be confused. Memorize. These are the units of momentum. Also, the direction of an impulse is the direction of the applied force. Be careful, because it doesn't have to be in the direction of either momentum. Let me give you an example of that. If the ball's going this way, and it strikes a wall, and after striking the wall, the ball is now going this way, did this ball experience an impulse? Yeah, it's clearly a change in direction, There had to be an impulse. But the force from the wall would have been a normal force, and it would have been this way. That's the direction of the impulse. The impulse isn't in either direction of the momenta. It's in the direction that the momentum changed. Does everybody understand? I'll say it again, because it's worth writing down. Impulse is about a change in momentum. So the direction of impulse is in the direction the momentum changed. That would be the direction of the force on the object. I want to reiterate, momentum is very intimately tied to direction. It's what makes it a powerful unit for us for study. Energy didn't have direction in it. One of the things you guys have a tendency to do wrong is to not know which side to use in a given problem. The problem will ask about work. You'll look work up on your equation sheet and pick whatever equation happens to be there, whether it's the right one or not. And sometimes you will stick with that regardless of how futile the effort is. It is always going to be easier to use the effect side if you can. Look for things that suggest you can deal with the effect side. Look for velocities. Look for changes in velocity. That's going to make doing those problems easier. They have to tell you stuff about forces in order for there to be anything about the causal side. You have to be looking for time intervals or displacements. If you don't have those things, it's a good chance they weren't there. Focus on velocity. I'm going to give you an example of something that really needs to be focused on velocity. And we'll see if you can figure out what I'm getting at, okay? If you were asked to find the impulse exerted on the ball from the table, your choice is either to find a way to measure force and time, or find a way to measure initial and final velocity. Did you have a stopwatch? No stop. I said all I can use is a meter stick. And there's certainly no force meter there. Agreed? No pressure plate. This is going to have to be using the effect side. You need final and initial velocity. But luckily you have an entire other unit from which to work. What kind of energy does the ball have when it's dropped? What kind of energy does it have just as it hits the table? I believe it has energy just as it hits the table. Kinetic, yeah. I believe as it hits the table, it's got kinetic energy. In fact, I'd say this is the initial amount of kinetic energy it has when it strikes the table. Does it have the same amount of energy when it leaves the table? No, I don't think so. How do we know? So there's a final amount of kinetic energy that is less than the initial amount of kinetic energy. And then there'll be a final amount of gravitational, correct? I think you should be able to use the gravitational potential energy to figure out what the velocity was. You should be able to. You had an entire unit on it. Probably something like mgh equals 1/2 mv squared. Yeah, that's how these things work together. So do you understand what I'm kind of expecting now to see you do? This is a laboratory activity, so probably G would be better using 9.8 because we're in our classroom. So raise your hand if you kind of have a direction on what to do now. It's not very many hands. That's too bad. So I'm thinking that I'm going to have mgh initial equals 1/2 mv initial squared. This should give me how fast the ball is going just as it strikes the table. And then it leaves the table with 1/2 mv final, rising to a height that is less than before. We measured this and this. I gave you the mass. I think you should be able to tell me the initial and final velocity from this. In fact, looking at this problem, you should be able to tell me the impulse from the table. You should be able to tell me the net work done by the table. And something else that you may not have thought about, the percent of energy lost. So raise your hand now if you have a better understanding, better direction what to do. Who knows how they're going to find the impulse now that we've had this conversation? It's a few of you, not as many as I'd like. Who's going to be able to calculate the net work? I hope so. That one's pretty easy. Who has a method for calculating the energy lost? So you need one? This would give you the fraction of energy lost, which you would then convert into a percentage. So if you've never done like a energy lost or a something lost, heat lost, something like that, it's final minus initial divided by initial. I do want you to try this because I want to do something with this today. We might not get to it today, but try it out. See what you can get. Work it out. Make sure everybody at the tables have the same answer. We'll walk around in a minute. Help me out for just a minute because I want to make sure we don't make a certain mistake. So you guys who have kind of figured out the velocities, how fast is it going just as it hits the ground? No. Root of 20. Right, or root of 19.6 because we're using 9.8. So 4 point what? And how fast does it leave the ground? 3 point what? Now, when you were asked to figure out the impulse exerted on the ball from the table, did you begin that portion of the problem by deciding what direction you're going to call positive or negative? I hope so. So what do you want? Upwards to be positive or upwards to be negative? Okay. We'll go with upwards being positive. So that suggests you did 0.15 times positive 3.8 minus 0.15 minus 4.4. This should be the impulse, the change in momentum on the ball. And it's positive, it's upwards. Any question about that? This is the force experienced by the ball. And that force not only did applied an impulse, but it did work on the ball by taking energy away. All right, that's good enough for now.